All right, so let's talk about thermodynamics and the law of thermodynamics. Thermo just means heat, and dynamics means movement. So it's the law of movement from heat. So first, before we do that, just want to make sure you guys know what systems are. So these are just sets of interconnected parts, right? And so it has all the objects involved in the energy transfer. So if you look at a car, that's a whole system going on there. But you can make it a lot simpler than that. You look at a bike, that's a whole system there. You look at a pool table, and all the billiard balls and the pool cues are part of the system, right? So that's kind of what a system is. So open systems is where it exchanges both matter and energy with its surroundings. Okay, an example of this is Earth. Earth is like its own system, but it does exchange matter with the environment. It also exchanges energy. Obviously, takes a lot of energy too, because we get our energy from the sun, right? Then there's a closed system, and that's where it can't exchange matter with its surroundings, but it can exchange energy. Okay, so that's like a closed can of soup. You can move energy into the soup, you can heat up the soup, but you can't move matter if the can is still closed, okay? And then there's isolated systems, and that's just where no energy, no matter is exchanged with the surroundings whatsoever. We don't have a lot of examples of that because it's very difficult to get an isolated system. So the first law of thermodynamics, you guys know it. I've said it a bunch of times now, and that is energy can't be created or destroyed. It's just transformed from one form into another, or one object into another. So you guys already know that one. Also known as the law of conservation of energy. But of course, we know that energy can't disappear or just appear, right? It is because, well, if energy seems to just appear, then it's because it's already been stored in something, right? And it doesn't just disappear, it goes into other things, right? The energy that my vocal cords are using right now is being transferred into sound. And sound is really just mechanical energy. It's just moving particles around in the air so then you can hear me, okay? So just so you know, it doesn't disappear or just magically appear. The energy was already there. It's just stored, or it goes into a billion different things. Okay, second law of thermodynamics is the one you don't know. And that just states that heat always flows naturally from a hot object to a cold object, right? What happens when you're boiling water? It starts to float up, right? Because it needs to go into colder spaces, and it starts to float around because the water's so hot, so it's trying to spread out itself out as much as possible. Okay, what happens when you're really cold and you're by a fire? You go closer to the fire and it heats you up, because that warmth from the fire is going to go from that hot place right where it's in the fire, and the heat is going to travel to you because you're much colder. Okay, if you have an engine, then the heat in the engine flows from high temperature to a low temperature area. And that's actually how we convert heat energy to mechanical energy, is by converting heat and making it flow to a cooler area, or, well, really just naturally does that. So we don't even need to make that happen. And that can be converted into mechanical energy. That's how our engines work. That's how we make our cars move, okay? But then again, a lot of machines do give off heat energy as waste as well. So if you feel something getting hotter, that's, something like a vehicle, that's because that's actually waste heat. You can't channel all the heat into just the mechanical energy, because again, it just goes to cooler areas around it. So you can't always control exactly where it goes, okay? And no process, especially with heat energy, can be 100% efficient. So you're always going to have some energy that's remaining in the form of thermal energy. Okay, so talking about that, we're going to go on to efficiency now and what that means. Efficiency. What is efficiency? Well, all machines or engines that produce mechanical energy, they can't be 100% efficient. They just, all the input energy that you input into it, it can't come out, right? You're always going to lose energy to something in the environment. So let's talk about useful energy. That's the type of energy needed to do the work that's wanted to do. And then all the other types of energy are considered wasted energy. So a car is designed to move, right? So all the energy put into a car is designed to make it move. So if a car makes sound, that's not helping it move, therefore that is wasted energy because it does take energy to make sound. Okay, so the energy is just all the initial energy sources used to make something do what it's supposed to. And then that useful energy output is the desired energy needed to do the work. So the wasted energy is all the other types of energy that don't contribute to making the machine work the way it's supposed to. Okay, so for example, a light bulb, there's electrical energy input into it. And then of course the useful energy that we get out of it is light. The wasted energy is heat. Now, we've gotten a lot better with light bulbs, but if you think about light bulbs 100 years ago, like the vast majority of the energy given off by old light bulbs was heat. They got so hot, and barely any of that went to actually light. So that was one of the most inefficient designs ever. So thankfully, we've gotten a lot better with light bulbs. So I want you to think about these guys. What kind of energy is going in? What kind of energy is coming out? And what would that waste energy be? Okay, let's first look at the iPhone right here. So the iPhone, usually electrical energy is being input, and what's its function? To give you electrical energy out, to give you light, to give you sound. So there's not a lot of waste energy here because a lot of the things you get from the iPhone you want. However, sometimes they can get kind of warm if you use them too much, so there is some energy lost to heat there. What about a microwave? Well, heat energy is definitely not the loss here because, again, we want the heat in this case, right? So the input energy is electrical, that's why it's plugged in, right? And the output energy is heat, so what could have been waste energy here? Well, not all the heat energy is good, right? Some of it goes to the atmosphere rather than just to the food, and it probably loses some energy to sound. Motorcycle here, any sort of engine is always, the output energy is always mechanical. You want it to move, right? So it's usually heat energy that's put in, especially if it's something that's being powered by gasoline. And then, of course, what you're losing from there, you get heat energy lost, right? Because we know engines heat up. So heat energy is being lost as well. Some of the waste energy definitely going to sound, stuff like that. And then a fan, so designed to do the opposite of the microwave. It's definitely being designed to cool things down. Okay, but of course this is called mechanical energy because you want the fans to spin, of course. So that's mechanical energy, that's energy of movement, right? So we put electrical energy in, it gives us mechanical energy and cools us down. So I'd say probably the biggest culprit of waste energy in a fan is just the sound. All right, so remember that machines are just designed to convert one form of energy to another to accomplish a specific task. So efficiency is just measuring how well did it accomplish that task. How much of the energy we put into it went towards accomplishing that task, and any of the energy that didn't accomplish that task is known as waste energy. Okay? So it's really that ratio between the useful output energy and the total input energy, and then we make it into a percentage, so then we multiply it by 100%. So here's our general efficiency formula. It's equal to useful output divided by total input times 100, okay? And so it's a ratio. It doesn't have any units until you convert it to a percent. So the energies have to be in the same units when you're doing this. So the output and input energies both need to be in joules. They could both be in kilojoules. It doesn't matter as long as they're in the same units. And just a little hint, because sometimes people are like, I don't know what the input is, I don't know what the output is. You should never have more than 100% efficiency. You won't even ever have 100% efficiency. Even the most efficient things in our universe are not 100% efficient, right? A bicycle is one of the most efficient machines, and that's still only in the 90 percentile. So just so you know, if you get something over 100, you probably put them in the wrong place and should switch them. Okay, let's look at our different ways to calculate percent efficiencies. We're basically doing it the same thing over and over, but we're just looking at the specific conversions. So there's a situation where I have total mechanical energy that's total mechanical energy that's being converted to useful mechanical energy, okay? So when you are trying to move one thing to make something else move, okay, I know that's kind of weird, but think about windmills, right? Windmill farms. We will try to make the windmills move, and that's mechanical energy, but then we convert that into more mechanical energy, okay? So, again, it's always output divided by input. So you can use energy or work. It doesn't really matter because, again, we know that work is change in energy. So they can basically be considered the same thing. So, of course, we have our useful output of mechanical energy. Oops, I didn't mean to strike through it there. Divided by total input of mechanical energy. Let's just go over an example because it's going to be way easier. So we have an electric motor using 670 kilojoules of electrical energy to generate 595 kilojoules of mechanical energy. So what's the efficiency? So how much of this energy is input into this machine? It uses 760, so that's how much is being input into it, and it's kilojoules. How much is being output? Well, it's generating that 595 kilojoules. That means that's the output there. So 595 kilojoules. There we go. They're both in kilojoules. So you know what? I'm just going to leave it like that. You do not need to convert this to joules. If you wanted to, by the way, you'd multiply by 1,000. But I don't need to do that. Okay? So again, if I want efficiency, I need output over input multiplied by 1,000. I think I said 1,000. I meant to say 100. Multiply by 100, not 1,000. All right, so to get that, our output was 595 kilojoules divided by the input, which was 670 kilojoules. I take that and I multiply it by 100. When we do that, we get 88.8%. We're still looking at significant digits, and in this case it is supposed to be 3. There we go. So there's the efficiency. So that is actually a really nice efficient system. So then what if we're transferring thermal energy to useful thermal energy? Okay, so this is like the microwave where there's thermal energy going in, and then not all the thermal energy coming out is useful, but some of it is. So again, here we still have output over input, but now it's just the output is heat and the input is heat. So you can't always just kind of rest on the laurels of, well, this is always output and this is always input. You really just have to read the question and try to figure out which is output, which is input. Again, a nice little trick to that is knowing that the output energy is usually smaller, well, always smaller than the total input energy. So we have heating, we're heating a pot of water. We have 2.00 times 10 to the 3 joules of heat was supplied by the stove, but only 5 times 10 to the 2 joules was actually gained by the water. Okay, so I want to know what the percent efficiency was. So our input was 2.00 times 10 to the 3. And our output is 5.00 times 10 to the 2 joules. Just a little note, if you don't know how to put scientific notation in your calculator, make sure you email me so I can maybe try and do a demo on that. I just can't do it on here right now. But hopefully you do. We did teach you that before we had to leave class. Also, when you have smaller exponents like this, you can change these into their actual numbers. So really, this one we just move it back 3 times, so that's the same as saying 2,000 joules. This one we move it back twice, so that's the same as saying 500 joules. So you can also use that in your calculation, okay? So my efficiency is equal to output divided by input times 100. So my output is 500 joules. My input is 2,000 joules. And I'm multiplying that by 100. And in that case, we just get 25%, or for 3 significant digits, we get 25.0%. Okay? And then we'll go over if we have thermal energy being transferred to useful mechanical energy, or vice versa. This is a very, very common one. Pretty much most machines we go through is having thermal energy being converted to mechanical energy, or at least the things that you think of as machines often do this, okay? So again, it's just the useful output divided by total input. Okay, so if I put in mechanical energy and that produces heat, then you're going to be using this guy. But if you put in heat and that produces mechanical energy, like in a car, then we got this guy. Okay? And so it's still output divided by input. So I'm not going to go over an example for that one because I just want to go over one challenge question. And then I'm going to be done talking, if you can believe it. Okay? So you pedal your bicycle up a steep hill, thus gaining gravitational potential energy. Okay, that's important. You gained vertical distance of 25 meters, so you went up to a height of 25 meters. Then coasted down the hill, transforming gravitational potential energy into kinetic energy. Okay, so at the bottom of the hill, you're coasting at a speed of 13 meters per second. And then the combined mass of you and your bicycle is 68 kilograms. What was the efficiency of the transformation of your gravitational potential energy into kinetic? What's happening? Okay, so your input, the total that you input, it was all the energy to get you up to the top of the hill, right? So your input energy is technically the gravitational potential energy that you gave yourself, okay? So that is your input energy. This is your potential energy that you put into that. And then the output is, of course, the kinetic energy you get going down there. And of course, we know, or at least so far, we have been calculating situations where all potential energy is being converted to kinetic, which you know is a little bit of a lie. I'm sorry. But, you know, we're just doing that for now. We can talk about friction, though. But we know if you're biking down a hill, most of that energy is going to go into kinetic energy. But guess what? Some of it's going to be lost because you still have tires along concrete or grass. And that is just going to slow you down just a little bit. So I want to know how much energy was lost. How efficient is this? So here I actually have to find my potential energy and I have to find my kinetic energy in order to be able to calculate efficiency. So let's find our potential energy, which is mgh. Okay, so that is 68 kilograms times 9.81 meters per second squared times the height, which was 25 meters. That's a tall hill. Oh boy, it's gonna be crazy. Okay, that is 16,677 joules. That's a lot of energy. I'm not going to worry about significant digits yet because I'm not at the end. Okay, I'm not going to worry about that till the very end. Let's do kinetic energy, 1/2 mv squared. Okay, so that's 1/2 times the mass, which is 68 kilograms, times my velocity, 13 meters per second. And I'm going to square that. And I get 5,746 joules. Okay, so we definitely don't have as much kinetic energy. So this, since bikes are so efficient, I wouldn't say this is just being lost to friction. This person definitely had to have hit the brakes, which makes sense if you're going on a 25-meter hill that is huge and then going all the way down. If you don't apply the brakes, oh my goodness, how fast you're going at the bottom, you'd like probably kill yourself. So let's calculate the efficiency now. So it's our output divided by our input. Okay, so in that case, it's our kinetic energy divided by our potential energy times 100. So the kinetic we got output was 746 joules. And our input was 16,677 joules. They're both in joules, so that's good, times 100. Oh, and I just barely have enough room down here. Yeah, this is not very efficient, but they probably had to apply the brakes. Okay, here I only need 2 significant digits, so my final answer is 34%. And there we go. We're done. Okay, so something like that with a bike. Usually a bike is very efficient. So that just means that they applied the brakes, which means a bunch of the energy went to heat energy, because that's how you brake, right? It's mechanical energy and then turns into heat energy. We don't need to get into all that, but yeah, I don't blame the person for applying the brakes though, because 13 meters per second is already super fast. I wouldn't want to be going that fast on a bike. So anyways, there you go. That is efficiency, thermodynamics, and my friends, we are done the physics unit. I know, I'm crying too.